Happy Tuesday again. All right, so we've got Project Zero coming up due Thursday. How's that going for everybody? Thumbs up, thumbs up. Head down. All right, cool. It's hopefully an easy start into some of our projects. They'll get a little bit more interesting as we get more stuff under our belt. So should be lots of fun. And then we're going to talk about inheritance more. So we did our arrays and vectors. Now we're going to jump more into inheritance. And then we'll pick up Project 1 this Thursday. So I'll go over the solution for Project 0. I probably should have put these backwards here, but that's okay. And then we'll talk about the next project. So hopefully you did some inheritance, right? Back in CIS 150. This is one of the ideas with object-oriented programming is that we can make things inherit. Right? And we got through a good amount of it, right, with rectangle and polygon. This idea that we can override that behavior. That's the big thing here, that if we are a type of our parent class, we can change the behavior, right? We can be a special version of it, and we can even do different things. Right? If we want different behaviors, we can get different behaviors back out. And then while we're running, nope. This is the wrong, oh my goodness. Come on, Visual Studio. This one, we did arrays and vectors. We didn't do the polygon one yet. I wonder you guys will look at me like I'm crazy. All right, we didn't get there. That was a different class, sorry. Let's try that again. Let me make a new project. That'll make this easier. This is week 5. All right, week 5, inheritance. That's what I have to do. Put it in the right spot here. Okay. All right, now we're good to keep moving. So we did our objects and classes first. That's right, okay, we came back for pointers. I gotcha. I've not had enough coffee yet this morning. These late nights are fun with early mornings. Usually I try not to get up till like noon, so getting here early has been a little different. All right, well, let's make a class. Should we make a polygon class? You guys like polygons? How good are you at math? So it turns out I don't remember how to calculate the area of a trapezoid. That one's a little hard to do, depending. So let's take a look at polygon. Yeah.
Is it meant to be on the screen?
It is. Oh man. Yeah. You should be able to see my screen. Okay. There. Thank you. All right, I'm going to switch over to this one, this purple can. The coffee's not cutting it yet. That's why I got this one on the way. All right. So we have some private attributes and some public functions. Maybe we'll come back to some private functions as we go. What sort of things do we know about polygons? What kind of attributes might a polygon have? Yeah.
Number of sides.
Yeah, number of sides. So we probably have an int for number of sides. What else do you think we know about polygons? If we know how many sides we have, what else do you think we know about the sides?
Perimeter. Length of side.
Yeah, so if we know the length of each side, we could get the perimeter, right? I think that makes sense. So maybe we have then an array list. So array lists are better, right? So make a include vector. So like a vector of, these are probably doubles, right? Because I don't know what sort of length these are going to be. I don't know if they'll all be whole numbers or not. We'll do a namespace. Vector of doubles, we'll call side lengths maybe. Okay, so we know how many sides we have, and we probably know the length of the sides. And from there we can calculate the perimeter. Other than that, It's really hard to know a lot about other things about polygons, right, without knowing what specific shape they are. But this should be any sort of polygon, right? So if we want to make a constructor, right, so we can have a polygon constructor that takes merely an argument for how many sides? Number of sides. So this number of sides is my number of sides. And then, right, the constructor's job is to give values to all my attributes. You don't want null things. So let's initialize our vector here. So our side length then can equal the vector of double. And if we know what size it is here, we can allocate how big it should be, right? We can say how many are going to go in here. I don't need to give it all the values necessarily or other vectors, but we got lots of fun overrides in here. But we can say, hey, how big should this one be? Okay, so let's give it the number of sides. And then we should go through and give it some values, right? So then maybe for int index is 0, index is less than my side lengths, index plus plus. Take our side lengths, and we're going to push back a 0. Less than side lengths. No, number of sides. There we go. I was really confused why that wasn't working. Number of sides. Right, so we can go add that many zeros to our vector. So now I should have a bunch of zeros ready to go, waiting for me to tell it what the length of my sides are. Then we need a way to go and set our side lengths. Right, so we can have probably a void method. Probably don't need to return anything here. Set side length. Given an int for length and a double for length, and then an int for side index. Right, we want to make sure we know which side we're setting. So side index 0, side index 1, index 2, index 3. This might be a little tricky because we didn't number them very well for people, but hopefully they can figure it out. So we'll take our vector, or our side lengths. Side lengths, come on. At the side index, and assign it the length. Right, it's pretty straightforward. We could sanity check the side index to make sure they gave me a valid index, but it's going to crash on me anyway if you give me a bad number. So I don't think we have to do lots of extra work ourselves. Like, we probably don't need to throw out our own exception. We could if we wanted to, but vector's already going to do that for us, which is nice. And then maybe a double for get side length, given an int for the side index. We can just return my side lengths at the side index. So we can make a polygon, we can set side lengths, we can get side lengths, and then maybe the perimeter. Double get perimeter. So we need to sum, right, our vector here, and then return that. So the double for sum is 0 for double side lengths, sum plus the side length. Then we can return the sum. Okay, we can do a quick loop through, add them all together, return that. We okay so far? All right, so polygon's not too bad, but what if we wanted to make a specific kind of polygon, right? And we don't want to reinvent the wheel. We don't want to do more work than we need to, right? What about, say, rectangle? Is rectangle easy enough? So we make a rectangle file. Now, you don't have to put them all in separate class files. I like doing that because it makes the history look really nice when I look at individual class files. Some people aren't fond of that, and that's okay. It's not going to hurt anything. So we're going to include, then, my polygon class, right, which essentially copy-pastes it. So having all the code in here is a little bit ugly rather than a separate CPP file, but then it's harder for me to test. You can still test it that way, you just have to click a lot more buttons, and that usually confuses people. I don't like to have to click a lot of buttons. So this is not the most proper way to put all your C++ code in your H files, but it's easy for our purposes, okay? We'll make a class for rectangle, and then we want to inherit from polygon, right? We want to be a type of polygon. So we'll have our private section, we'll have our public section, right? So things about rectangle. Do we need any other special attributes to be a rectangle if we are a polygon? Remember, inheritance creates an is a relationship. So a rectangle is a polygon, which I think makes sense for our definitions here. A lot of times when we're teaching people how inheritance works, you start to want to inherit everything. And you get some really weird looking solutions where you inherit from things that don't make any sense with an is-a relationship. Right? I had someone was doing a Yahtzee project in my other class, and they wanted to inherit from dice for their player because their player had dice. You can have dice without being dice. Right? So inheritance was not the right solution for that. It sort of works because code lets you do all sorts of crazy things, but it was not good design, right? Because if you are a type of that, then you might want to use inheritance. If you just have some of those things, that's fine. You just have them as attributes. Right? You can have an attribute for your dice. You don't need to be a dice to do that, right? So it's just a tool. It's not the everything tool. Just a warning there. Right? So I don't think we need lots of interesting, unique attributes in rectangle because we already have our side lengths. We can figure out all of our side lengths, those sorts of things. But what do we need? Right? If I want to make a rectangle here, right? So let's go include some files. So let's include our polygon, and we'll include a rectangle. And so if we wanted to maybe ask for length and width, right? Enter a length. And we'll get a double for length, and then we can see in the length, and then we can do the same for width. For width. And then make a rectangle. So I don't know. So rectangle equals a rectangle. I don't have a way to pass them to the constructor. Okay, so I can make a constructor, rectangle equals a rectangle. Did I spell it wrong? There it goes. Default constructor rectangle cannot be referenced. It is a deleted function. Well, that's a fun error, not a very helpful one, right? But let's think about it for a minute. So if rectangle is a polygon, and polygon has a constructor that needs the number of sides, is there a way to make a polygon from rectangle without a constructor? Right? How does the polygon constructor know what the number of sides is? It doesn't, right? Because remember, if you are a type of, all the code has to run. So you have to run the constructor in polygon in order to create a rectangle. So the default constructors could work if you have default constructor. So, or if you don't define one, here you get a default constructor. Let's add in some slashes here real quick. And now my red goes away. If you don't make a constructor in C++, you get a default one, which is generally garbage. They're almost never useful, right? Because you get bad values for things. You want constructors because their job is to give values to all your attributes. So we will almost always write one, because they're useful. Right? And then we can set what those default values are. But if you have one that takes parameters, you can't make an object without giving it the parameters. So I can't make a polygon without telling it how many sides it has. So in our case, when we write the constructor and we say, hey, rectangle is a polygon, somehow, somewhere, the polygon constructor has to get called for it to exist. Right? Because this is the code that has to run in order to create a polygon in memory. And if we're a rectangle, we are a polygon. So we have to call our base class. Right? There's like 3 different terms people use for these things. I don't know why we have so many different terms. You have a base class and a derived class. You have a parent class and you have a child class. You have a superclass and you have a subclass. I don't know why. Well, whatever. I like super and sub. Base is also used, which confuses me. I don't like base and derived, but that's fine. Other people do. And then parent and child sort of makes sense because we think of inheritance sort of that way, right? You come from the parent type here. So because we are a type of polygon, we have to call that polygon constructor. So we need a constructor then. So I need a rectangle constructor. Now, rectangle doesn't need to know how many sides it has, right? Because we all know how many sides a rectangle has. If we wanted, we could ask for a length and width in this constructor. Right? So when you're creating a rectangle, you could tell it, hey, here's your length and here's your width. Or we could go and set those lengths later. Either one's okay, right? We got options here. So what do you want to do? Do you want rectangle to take no arguments, or do you want rectangle to take a length and width argument? We can do it either way. All right, so we'll take some arguments. So we'll take a double for length and a double for width. And now it's telling me right away that no default constructor exists for class polygon. So as soon as I added my curly braces here, it's like, hey, you can't do this because you haven't called a constructor. So by default, it's going to try and call a default constructor, a no argument constructor. But one doesn't exist in Polygon. Right? We don't have one. If we added one in here, right, if we just had Polygon now our red goes away. Because it says, oh, okay, you must want to call the default one the no argument constructor. But we didn't really want that, right? This is not very helpful. And then we don't have a way to change the number of sides. And with our number of sides, it doesn't really make sense to be able to change that. Like once you create a polygon with n number of sides, it's probably always going to have that number of sides, right? If you want a polygon with a different number of sides, you should make a different polygon. So some of our attributes shouldn't be changeable. Right? This idea of them being read-only, right? I don't need to give you a set number of sides because that doesn't really make sense. And then I have to change my vector around and things will get really confusing really quick. So if we have that constructor, we have to go call it. Is it base? No, is it rectangle, polygon? I can never remember the syntax here. I think it's this. So we say, hey, when my constructor gets called, call the polygon constructor, and here's what you're going to give it. In this case, 4. Now, you could, right, if you had an int for a number of sides, and this is pretty common, you'll say, hey, I'm going to give it my number of sides argument here. You can say, hey, I'll take an argument that my parent class needs, and I'll just hand it right off to the parent class, because it will do all the things it needs to do with it. Now, for our number of sides, that's kind of silly, because we know how many sides a rectangle has. When we look at some other examples, you'll see we're going to not pass in a hard-coded number. We're going to just pass in the argument for our constructor. So I'll just take it, and I'll hand it right off to my parent class. Okay. Now all the red goes away because we're calling the polygon constructor. Then I can go through and do my set lengths and set widths, or right, but really it's set side length here. So I can go and now we could go and call our own methods, right? We have public functions here for set side length, but I don't have access to the side lengths vector, right? This is my private section here, so I can't go to side lengths, right, and do anything here. Side lengths dot at 0 equals length, right? It's going to yell at me. It says it's inaccessible. Member polygon colon side lengths. It even tells me where it is. That's handy. Is inaccessible. I don't have access to it. Right? That private attribute means no one else can touch it outside of my class. If we wanted to, we could let our child classes have access to our attributes, to specific attributes. There's a level of access between private and public. So we don't need to make it accessible to everyone, but maybe we want to make it accessible to just our child classes. We could call it protected. So we've got a protected section here. So if I move side lengths to protected here, this is all, oops, sorry, not the pound sign, all child classes, or should we say derived subclasses have direct access. So now I can say, hey, side lengths at 0, do this. Side lengths at this, do this, right? That's one option. So probably at, what, 0 and 2 for length, and side lengths at 1 and 3 for width, right? Because you want to keep these in pairs. And I can do the direct 0, 2, 1, and 3 because this polygon constructor has run. So before the code ever gets to line 11, the polygon constructor runs. So in that order of, like, if we wanted to watch this in debug mode, which y'all got to use the debugger way more often, because the last time we tried it, it didn't go so well. That's okay. That's what you got to practice. It's super handy to step through your code one line at a time and see what's happening. So let's, we don't need to do that right now. Okay, so here's our rectangle with length and width. Length and width. Hey, there we go. We got to here. So if I run this in debug mode, we'll pause here and try it. What's the length? How long is our rectangle? 7. And how wide is our rectangle? 2. All right. Now it paused. It said, okay, I'm about to call this constructor. So I got 7 and I got 2. So let's step into our code, not step over, because I want to see what's happening. Now we go to the rectangle constructor. And now I can step into my code again. And now I'm in the polygon constructor. Right, before any of the rectangle code runs, the polygon constructor has to run. And we told it, hey, number of sides, well, that's garbage for a second, it'll fix. Now we say number of sides is 4, right? So we set our number of sides, set up our vector, we push back a bunch of zeros. Uh-oh. I did it bad. I got too many zeros. I didn't need to push back a bunch of zeros. That would have been if we started it empty, right? I started it at the right size here. Probably could, at the index here, set them to zeros. Now, we should get zeros by default. I just always hate like relying on that to work here. This is probably silly. Not needed. Makes me happy. All right, there. So let's stop and run. So we saw we had a problem. We'll try it again. Totally did that on purpose, right? To illustrate, this is why the debugger is great. So 7 and 2. Step into our code, step into our code. Here we go. Now we set up a vector of side lengths. And we have 4 here. Great. And we're going to go set them all. Oh, I stepped out. That's all right. We set them all to 0. They were already zeros. Now our rectangle code can run. Now we set the side lengths, set the side length, set the side length, set the side length. So in my this pointer, right, I don't see the attribute of side length accessible here. It's inside the polygon side lengths, right? Because it's really part of polygon. I just have access to it. So when you're looking at your pointer to try and see where all your values are, it's in the parent class definition. Right? It kind of groups them all together for us. So now I can see I've got 7, 2, 7, and 2. I step over, and then we're done. So should probably be able to figure out the perimeter. Perimeter, your rectangle is rectangle.get. Where's my other methods here? Dot. Why am I not get perimeter? What? It should suggest that for me. Why is type ahead broken? That's sad. It's inaccessible. Did we do that in the public section? We did. Get perimeter. Why am I not getting perimeter? Well, that's sad. Do you think search online will find anything? That's not helpful. Not helpful. So we haven't grabbed all the methods yet. So when we do inheritance, and this I should just go open up the Zybook here because I can never remember what that syntax is. Or we could go Google it too, but this is, we could check out our textbook. Oh, come on. There we go. Let's see if I find the right URL. Derived classes. Ah, there we go. I need to say what I'm taking from that derived class. So I want all of the stuff that was from it to also be in mine. So I can be a polygon, but not get all of the public methods here. So if I want all the public methods here, say, okay, now I want all the public stuff from polygon. Now we get all the public functions. They become accessible. So we have to specify that yes, I want to be all of the type of this, and I want them all to be accessible. I want to grab all those public functions and make them look like they're rectangle functions too. Now, my type ahead, like IntelliSense knows that it comes from polygon, not from rectangle. Right? It says, hey, that's polygon get parameter, but it works for rectangle because rectangle is a polygon, which is fun. All right, so now I should be able to get the parameter out. And again, we're just testing it the poor old sad way here of punching in numbers and looking at the output here. But that's okay, right? We got to start somewhere. We could write unit tests later. 18. That looks right. 9 times 2. Okay, cool. So we can get the parameter out. Now, what if we wanted to make another kind of polygon? Can we make another kind of polygon? Or before we do that, what happens if I want to go change some of these side lengths here? Because I took all of the public functions here, I have set side length. What if I set, I don't know, 5 and side index 2? What's going to happen to my poor little rectangle if I change one side here? Should we put it in debug mode? So 7 and 2, and we go change it to 5. So if I step into my code, it's going to go set the side length. And now if I look at my rectangle, and I look at the side lengths, I have 7, 2, 5, and 2. I'm not much of a rectangle anymore, am I? So we've let a bad thing happen, right? So the other cool thing we can do with inheritance is if you want to change the behavior of your parent class functions, you can do that. You can say, okay, I am a polygon, but I want something different to happen when you call set side length. So we're going to add an override for void set side length. Is it override? No, am I putting it in the wrong spot? That's in the wrong spot. Set side. I can never remember the syntax here. I'm sorry. Where is it? Overriding. Where's the keyword? Where is it here? That's terrible. Where does it go? Computer. Did I just write it? Maybe I just write it. Set side length, given a double for side length and an int for side index. No, I gotta add my keyword. Did I not add the keyword? Overriding. Okay, that's it. Cool. So I'm going to make the function match here. So the name matches, set side length, and my parameters have to match here. So I've got the double first and then the int, right? The double first and then the int. So when you set the side length here, if you're setting length, I need to set both lengths. If you're setting widths, I have to set both widths. Right? So we can say, hey, if my side index, how about modulus 2 is 0? If they're the evens, 0 or 2. And then how about we set the lengths? Right? Otherwise, you must be the odds. We'll set the odds. We do it like that. So we've got access to side lengths here. We can just go set them. What am I missing? Where? Am I missing a curly brace now? I think my Visual Studio is going crazy, right? What's the error? Expected a curly brace. For what? That's the match. That's the match. That's the match. I think it's confused. All right, so now if I set side length here, this is rectangle set side length, right? The IntelliSense is telling me, hey, we'll run the rectangle version here. So let's give that a run. So if we make it 7 and 2, now we're ready to step into, so we'll step into our code. Now we're in the rectangle code set side length. And like we'd expect, it sets both side lengths. Life is pretty good here. This was fun. Now, but what happens if we didn't go this route of using protected? What if we left that in as private? Just for fun. Now all my code here gets upset for set side length. Well, that's okay. We still have the set side length method we could call. So we can call set side length, the length and 0, right? And then we'll call the width at 1, set side length, and then the width at 1, length, and width. So I can call my own set side length, but now this function needs to do something different. I have to call my parent class set side length, because that's the only way I have access to change those things. So to call the parent class version, I want to say, hey, I want polygon, : set side length. And I want to set, what is it here? I want the side length, and 0 is my index. So I can call my parent class version of this here by name. Say, hey, go to the polygon class, call this one here, because I've got access to theirs specifically. And we'll do this for 0 and 2, oops, and for 1 and 3. Runs the parent class. So I can call mine here with length and width. Why? Yeah, Visual Studio is real weird right now. Probably just need to restart it. It'll call my version. My version will call the polygon's version. So I'm overriding their behavior. I'm saying, let's do something different here. So we're overriding polygon version of this function. So if now we run it, let's do 7 and 2. And then we can step into our code. We'll see, okay, now we're in our version of set side length. Now we're going to call the polygon's version of set side length, and it's going to set, because this one has access, right? Polygon has access to the side lengths. So I can use that function to set both parts of my rectangle, right? To make sure that it stays a rectangle. And now life is happy. Because now our rectangle class is protecting the integrity of itself. You can't change the length of one side without changing the length of the other side. You can't change the width of one side without changing the width of the other side. So we're making sure that we're keeping things the way they need to be kept, right? That one okay so far? So we can change the behavior. We can override, but we can still use the parent class version. But it keeps someone who has a rectangle from using the right version. Now here's where it gets fun, right? We talked about these core concepts of object-oriented programming. Right, we've got encapsulation. We're keeping all of our details kind of in one nice, neat little package. We have abstraction. You work with the public functions here. You don't need to know the internal details. It just does what it's supposed to do. And then inheritance and polymorphism kind of go hand in hand. Those are fun words. So inheritance, you can create this is a relationship. And then when you have that, you can do this cool thing called polymorphism, which is a fun term here. Makes me think of the spell polymorph. But you can treat a child class as its parent class. You can treat things as the type that they are higher up in the chain. So with polymorphism, I can make, say, hey, I want a vector of, let's have polygon here. We'll call this my shapes vector. I've got to include, I should have all of those, right? Yep, okay, I do. Shapes. And then I can say shapes dot pushback. I can add my rectangle to my polygon vector, because a rectangle is a polygon. So it fits in the space that we are reserving for polygons, which is kind of cool. So I can go through and I can store all of these here in my vector, right? And I can do all my operations on them. So if I want, I don't know, for polygon shape in the shapes list, the shapes vector here, we'll see out perimeter of the shape is shape.getPerimeter. So we should be able to get the new perimeter back out here, right? When we run, you take out the breakpoint here. So if we wanted 7 and 2, it was 18, we changed it to 5, now the perimeter is 14 of that one. So it can treat it like a polygon, but we still get all this cool stuff that it does, right? And so if I make other kinds of polygons, let's make another kind of polygon here. How about a triangle? Can we make a triangle? Right, so class for triangle. Now, triangle, right, is a public polygon. Right? Get up, grab all the public stuff, make yourself a polygon. Oh, we got to go include that, don't we? Include polygon. All right. Now we're a polygon. So we'll make our private section, make our public section. Probably, again, we don't really need any private attributes. We could maybe if we wanted to, but it's going to be okay. So to make a triangle, right, we can write a triangle constructor. Triangle. Now, we know how many sides we have, but should we take arguments for A, B, and C? Length A, length B, length C. So double A, double B, double C. I think A, B, and C are terrible variable names here, but I don't know if side 1, side 2, side 3, does that make more sense? How about side A? Side length A. There we go. I feel a little better about these variable names now. B and C. Okay. It has to call the polygon constructor with 3 sides. Right, that's the first thing we have to do. So we can add in our colon, say, okay, call my superclass, my base class, tell it I have 3 sides. Then I can go and set my side lengths. Set side length of, here's side length A, and that'll be index 0, and then B and C. 1 and 2. Okay. Now, I'm not going to do any sanity checking to make sure these lengths are actually valid. I don't know the math for that. That's okay. We'll assume they probably gave me some decent numbers here, and it should work, right? So, is that it for triangle? Now we get the perimeter, right? Well, for things that are not just N-shaped polygons, should we be able to figure out their area? Like, I know I can get the area of a rectangle, I can get the area of a triangle, right? We can do that. We can have a double for get area. We can return my get side length of 0 times the get side length of 1. So I get the area of a rectangle really easy, right? Length times width. Should we be able to do that for triangle? How about a double for get area? Now the area of a triangle formula I have to go look up here. So area of a triangle from side lengths. Because it's 1/2 base times height, but we don't have the base or the height here. So we can do, where is it here? Didn't I have the formula? Was it, did I just miss it? Oh, Heron's formula. Yeah, I missed it here. That's a terrible, wow. The square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter times minus B times the semi-perimeter minus C. Sure, that's half the perimeter. We could do that, right? Or you could do 1/4 of the square root of this one, or 1/4 of this. Must be that foiled or something? Or something? It's been a while since I've done any math. So how about we stick with the semi-perimeter one, because that one seems like it might be easiest for us. Okay, so we need the double for semi-perimeter equals my get perimeter times 0.5, right, or divided by 2, whatever you prefer. Okay, so now we've got that. Now we need to, we can just return math dot, so we can include math, math dot, is it capital M? Math dot, we can just do square root now. Square root, there we go. The square root of my semi-perimeter times my semi-perimeter minus side length A, so get side length of 0. This one's going to be a little bit long here, right? But that's okay. That's the first one, right? Times the semi-perimeter of, oops, get the right number of parentheses here, of get side length 1 times the semi-perimeter of get side length 2. Why do I have so many parentheses? Where's that one match? Does that one line up? No, not enough. that one here. That's where I'm missing a parenthesis. One more parenthesis. Okay. It's a lot of parentheses to make things match here. So all of that, right, gets thrown in the square root. Semi-perimeter times, 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 times. I think we got them all. Order of operations is important here, right? We don't want to screw this one up. Oh, I finally found that thing about order of operations where I complain about the math teachers all the time. You remember that? No? Okay. I'll show it to you after. Just remind me. It's worth it, because the problem is math teachers are lazy and they don't include the multiplication sign. Really, they've let all of us down by being lazy and not including the multiplication sign. All right, so we can get area. That probably works, right? So if we give it, let's make another triangle here. So let's make a triangle, I guess. So triangle equals a triangle. Nope, triangle. And how about 3, 4, 5? Right, because I know that one is a right angle triangle and that one works. So I got to include triangle here. Include our triangle. Okay, make it 3, 4, 5. So that is 1/2 the base times the height, and I know base and height are these two, right? For a right angle triangle. So it should be 1/2 of 12, should be 6. Okay, so let's see. So we can see out area of your triangle. Triangle, there we go. Get area. All right, should we try that? So 7 and 2, area of the triangle 6. Hey, it calculated it right. That worked out nice. So it probably works for the other ones. I assume whoever this Heron guy is probably pretty smart, and he's been checked by other people who know much more about triangle math than me. Trigonometry. Does that count as trigonometry when you're doing the area of a triangle? Or is that only dealing with your angles?
It's just, yeah, geometry. That has the angles, it's trigonometry.
Okay. I know very little math. It's been so useful all the times in my career that I keep it all in my head. I worked with a guy once. He got a double major in math and computer science because he's like, it was only like 3 more classes because you take so much math already. And he's like, and I use it all the time. He was not sad about it at all, I'm sure. But math was interesting, so. So this is cool, but now when we have our polygons, our shapes here, right, this list of shapes, let me put that back. I can take my shapes and I can push back my triangle, right, because it is a shape, it is a polygon, it fits. But when I'm treating these things as polygons, I don't have get area, right, which is pretty sad. It's not there. Right? There is no get area function. Because in polygon, all I have is get perimeter, get side length, set side length. So if I'm not treating them as their child type, I don't have the get area function, which is kind of a bummer. Right? I wanted to go get those, but I don't have them. So there's something we can do. I'm glad you asked. Because I know that was bothering you too. We can add a function. Where is it here? And we can mark it as virtual. We can say, hey, I will have a function here. So in my public section, I'm going to make a virtual function. We'll call this virtual double get area. That's all you put. Nope, equals 0. Is that it? No. Yeah, now it goes away. Okay. So my virtual function for get area, it's if I leave it like this, it gets upset. It's like, oh, we never defined it. So it's not ideal here. You can give an implementation if you want. We could say, hey, return 0. It's probably not what we want here. But this, so the virtual keyword says this should get overridden. So I can mark it as virtual, so it should get overridden. So I can add my virtual keyword for some of these here, right? The set side length, because I do want to override this later. So we can mark it as virtual, so I can go and override it later, and it'll work out nice with polymorphism. So we'll have a get area. So now I can get, here's the perimeter and the area of the shape. Now I have a get area function, right? because I wrote a getArea function in Polygon. So I should be able to call getArea here. So these getAreas should override. Right, let's see if it works. So let's do 7 and 2. All right, so now we are at the area of the shape. We'll do shape getArea. So let's step into our code. Uh-oh, we're at the Polygon version. We're going to get 0 back out. 0 is definitely not the area of a rectangle. It didn't work. That was kind of sad. Didn't work for us. So for you to get the right version while treating it as its parent class type, we have to do a little bit more magic. This is where it gets weird here. So, and this is why we talked about pointers first. So to get this to work, when we make our objects, what's going on? We have to create them as pointers. Is it doing it in here? Is it doing it? I don't think it is. It didn't show it. No, that's fine. Yeah, I can add the override. Now I can add the override keyword. Yeah. Is it? I usually like SciBooks, but like this more interesting topic stuff, it just comes out like nonsense in their book. That's okay. Let's see. So yes, if I have a pointer of the type, there it is here. If we use pointers, we get more magic. So I want a vector of polygon pointers here. And I'll make rectangle pointers and triangle pointers here. Right, with my new keyword. And where's my triangle pointer? So new triangle with the keyword. Now, remember, I can't use the dot notation anymore. Once I have a pointer, I have to use the arrow notation. Or I can dereference if you still like the dot notation. I can do it that way, right? Dereference it and then use the dot notation, or use your arrow notation. Either way is fine, right? So now polygon pointer doesn't fit for polygon here. So let's do shape as a polygon pointer, shape get parameter, and shape arrow getArea, and arrow here as well. I like the arrows because it was obnoxious to do the dereferencing every time. I'd rather just do the arrows, but that's fine. Okay, so now we're using pointers. That's the only thing I changed, right? Should we try it? So let's do 7 and 2. Let's step into our function. Now we're at the getArea function of rectangle. So if we have a pointer at runtime, while we're calling this function, it will go find the one that is overridden, not the parent class type. So we told it it's a polygon. Hey, these are polygon pointers. But while it's running, if you call a function that's been overridden, it will use the correct base class or the derived class implementation. Only with pointers. That's why we got to talk about them first. So now we can take advantage of the polymorphic behavior, and I can get the proper getArea out from each shape, and I'll get my length and width. And life is good. Area of our 5 by 2, right, is 10. I think that's right for length and width. So if we're using pointers, we get the behavior. The right function runs. I don't know why. I wish I knew why. Should we Google it? I don't know why. Why do you only get morphic behavior in C++ with pointers? We'll see if Google can tell us. Stack Overflow. It doesn't answer the question. Why did this get so many votes? Let's see. When a virtual function is called through a reference or pointer, and the compiler cannot prove that the object referenced or pointed to is of runtime type with a specific known implementation of that virtual function, the compiler inserts code which looks up the correct virtual function to a call at runtime. This gets to be really fun stuff. So eventually you can take a compiler's class if you like this sort of thing. And I'm super glad people like this sort of thing because I like when my compiler works and I like when it does all sorts of magic for me. But essentially it's saying, go look this up later. Right? So when the code gets compiled, if we looked at the actual compiled code, it would say, go find a getArea function later, wherever that will be defined. When we compile it without pointers, it takes the Polygon version because that's the one it knows about. It's kind of messy. But that's sort of the magic here that happens. Super fun, right? Where is my override keyword? I'm really sad about that. I really thought we had an override keyword. It is, okay, it goes at the end. That's what it is here. I got it backwards here. So if we're overriding, we can add the override keyword. There, now I'm so much happier. Override, and override, right? Now we didn't need it in here, but it's nice to have it. Let's see, and I think if we take it out, let me, just for fun here, comment that out. Now, it yells at us and says, hey, we told it it's supposed to override, but it doesn't override anything. So it adds a little bit of checking for us at compile time. You're like, hey, I want to override something, but if you're like me and you typo things all the time, you had getArea, let's undo that, right? Now you're checking, adding the override check here is super helpful because it's like, hey, you don't have a getArea here. You're like, oh, well, I must have done something wrong because I really do have one. There it goes. Okay, now I can get the area. All right, the next cool piece we can do, so I had it started, so return 0 is kind of a little ugly here. You could also like throw an exception. That's one option. Some people throw not implemented exceptions, or we can do this thing where I say it equals 0. This equals 0 means it doesn't exist here. It is a pure virtual function. So pure virtual functions. Like there is no definition here to bind to. So it doesn't exist. So if you have a function that doesn't exist, you're going to have some trouble doing something like polygon. Polygon, new polygon equals a polygon of, I don't know, 5, 6 sides. Let's make a hexagon. Now it says, hey, abstract class polygon is not allowed. Function polygon getArea is a pure virtual function, or is pure virtual. It is function, okay. I can't read yet. So if you declare something as a pure virtual function, you can't create instances of that class. It's known as an abstract class. So having this pure virtual function makes the class abstract. Thank you, caps lock. So might seem a little silly. Why do we write a bunch of code and not be able to use it here? Why would we want an abstract class? But just like we're using it now, it has all of the shared behavior here, but doesn't really do all the things we want it to do. I don't want anyone using Polygon directly here. I'm only putting all the shared behavior in a class, so I don't have to rewrite it for rectangle, don't have to rewrite it for triangle. And we're going to do trapezoid in a minute. We don't have to rewrite it for trapezoid, right? All the shared code, because if you have the same code more than once, you should feel bad about yourself, can go into a shared class. And then we can make it pure virtual if I have functions that I don't know how to implement. Because with a generic polygon, I don't know how to implement getArea. I could return 0. That was an option. But it's a little bit ugly, right? Or maybe that's proper in math land, right? If you have an open polygon, can you return 0 for area? But if it's not, like if it is a rectangle, we don't want 0 back out. Or if it is a triangle, we don't want 0 back out. So depending on what we're doing in our code, right, depending on what solution we're modeling, we might have pure virtual classes, or these abstract classes, where I have some definition here, but not all of it, right? We can do that. So now I can't make a polygon. So can't create once it has a virtual function, or pure virtual function. So I'll just leave that commented out, because otherwise it won't compile. right? We okay so far? So we've got all of our shared behavior. Super fun. Let's see, keep going back here. Abstract classes, in is a versus has a, yep, and UML. So UML is great, our unified modeling language, and drawing a picture of how our classes look. Now there's fancy software that does all sorts of things. You can just Google like UML, class diagram, and Lucid Chart is like the first one that comes up because it's an ad related to it because they want your money, which is really cool actually. Visual Paradigm is a fancy tool. I don't know if people actually use this anymore or not, but does some cool stuff here. We can look at Wikipedia pages, sure, but I'll go to the Lucid Chart page here. Not the ad, I don't want them to have to pay money for this. I would feel bad about that. I want to create my own in a Lucid Chart. I don't want that one. Let's create my own. Let's see. Hey, the free plan. Okay, I like free. 3 charts, 60 shapes per document. Hey, you know, it's the freeware version, right? You get it for free. That's fun. Restart. I don't want to have to sign up. Oh goodness, that's obnoxious. So you could, and you can get all the cool tools that does fun things here to get your class diagrams. Class diagrams are great. Here's the super basic example. It's got 3 sections. The top has the class name, the middle has its attributes, and the bottom has the functions. That's super basic. So I do them in Word because I'm lazy, and I think that just comes out fine. And most everyone has Word. I think you've had access to it here. So I insert a table, a 3x1 table in Word. This is my UML class diagrams on the cheap. We also have Visio on the computers. Visio is a great tool for it. Does some fancy things too. I think we're okay with the cheap one, but that's okay. So I might have Polygon. Let me make this a little bit bigger here. So that's my class. And then when you're defining attributes and functions, some additional information you can give. You can have a minus sign for private. You can have a plus sign for public. Or you can have the pound sign for protected. Right? I think we've talked about this. It's not a hashtag because there's no name attached. Come on. All right, this is why it's obnoxious using Word here. My apologies. I just want the stupid dash. I don't want it as a formatted list. Stop creating bulleted lists. Stop creating bulleted lists. Can I untab this one? Hey, okay, there we go. We fought with Word and we won. So when I'm creating my variables here, I'll have and now the syntax for these is backwards. You give it the variable name colon the type, not the type first. So if you're used to giving the type first, like C++, you're gonna be very confused, but that's okay. So we'll say, here's my number of sides, colon init. Here's my side lengths. That is a vector of double. All right, those are my private attributes. Then I have my functions. So class name, attributes, functions, and you get the same definitions here. So we'll have public, Polygon. Now, arguments are still also backwards. So I'll have my number of sides as an int here. Right? I've got a Polygon constructor. I have a set side length, given a side length colon double, comma, side index, colon int, colon void. All sorts of fun things. So the next piece of information when you're doing functions is you have the return type. Again, also backwards. So this is it's a void function. It returns nothing here. Get side length, given a side index as an integer, will return a double. Right? And on and on and on. We would add all these sorts of things here. So this way I have a picture that describes my class. And if I give someone a picture, they've got most of the information they need to at least get the form of the class going. They might not know all the details, right? If I gave you triangle and said it has a get area and all you have is A, B, and C, you'd probably have to go look it up. That's okay. We can look things up all the time. You don't have to memorize anything, right? But you can give a picture. So when we're describing classes and collaborating with people, we have a shared language here, this unified modeling language to use to show pictures of things, which is great. So I can look at a picture and quickly see, okay, here's the attributes, here's the functions, here's how I've described this object here. Then we can look at it and talk about it without having any code written. Saves us a little bit of time when we're planning things out. So people love whiteboards, they love drawing pictures on whiteboards. This is something you can draw to sort of list these things out, these UML class diagrams. And if you remember, way back when, somewhere in here, it's in here, isn't it? Didn't we have UML? I thought it was one of the objectives in here. Is it the last class? UML. It's in there. Oh, it's in the description, not the outcomes. The principles of UML modeling are also introduced. Not an actual outcome. We don't have to measure it, yay. You probably did activity diagrams in 150. You remember doing activity diagrams? That was one of the outcomes. Really? That's really sad. We're supposed to do those things. Okay. So this is just one type of diagram that you can do with UML. All sorts of fun things you can do with UML. Right? Some people love it, some people don't. It's okay.
Use case diagrams.
Use case, yep. But not activity diagrams?
Call them activity
Really?
diagrams.
Okay. I thought that was the first one we did. And then you get to use case. But that's okay. You can do those too. Yeah, use case diagrams are fun too.
I remember doing use case for the final project. We had to make a use case diagram along with it.
Yeah.
But I don't remember an activity one.
I thought we did that.
Maybe it was early enough that I've just forgotten.
I only talk about it for like 10 minutes because they irritate me, but that's okay. We should look those up. UML activity diagram. And look, Lucid Chart. It's got a tutorial for it. What is it? He's got a fun video. That's oh man. Demonstrate the logic of an algorithm. Describe the steps performed in the use case. So the use case doesn't have the logic. This gets into more detail. You get actions, decisions, control flows, start and ends. This is super fun, right? This is actually like a pretty handy website here. Not gonna lie. Right? So here's the start. The client gets registered. And then they enter login name and password. If it's correct, yes or no, this is my decision. Your diamonds are the decisions. No, it goes back. Yes, okay, they get logged in. Settings are displayed. Ends. Then the client logs in. Cool. Or your account. Withdraw or deposit. Withdraw my decision point here. Is not allowed or is allowed? Okay, anyway, that was fun. That's about as much time as we spent on the 150, right? Yeah.
What were you going to show us about the math thing?
Math.
Yeah, you said to remind you.
Oh, yeah, at the end. Thank you. Yeah, well, we're just wrapping up, and I'll show you that. It's just the silly little post on Twitter about what is the right answer to this, and someone's like, I've taken all 3 calculus classes, and I know the answer is this, and someone else, I have 2 math degrees, and the answer is this. And they just argue about it, because math teachers are lazy and don't use the multiplication sign. That's all. Okay. We're doing pretty good? I think we're doing pretty good. Let's see, we got through all those. Yeah, so the last little bit, the pure abstract classes we'll talk about on Thursday. So we've got the project solution Thursday, the new project Thursday, and we'll finish up with abstract classes on Thursday. We should be pretty good. All right, thoughts, concerns? All right, let me end this here.